Welcome to the Explainer. Whenever we picture oil and gas extraction, a lot of us kind of just imagine these giant, cavernous, underground lakes of black liquid, right? Like they're just sitting down there waiting for a massive straw to be poked into them. But the reality of petroleum production is actually way more fascinating and honestly, a whole lot harder. It is definitely not about underground oceans. We are talking about a microscopic, high-stakes game of pressure, fluids, and solid rock. Okay, let's just take a really quick look at our roadmap for today. We're going to cover 1. Meet the production engineer, 2. Inside the petroleum reservoir, 3. The near wellbore zone, 4. Journey to the surface, and finally 5. Well deliverability. Section 1. Meet the production engineer, masters of extraction. Let's introduce the unsung heroes of this whole operation. People outside the industry often blur the lines between all the different engineers out in the oil field. But if you break it down, there are 2 really distinct worlds here. You've got the reservoir engineer, who takes a super long-term view. They're managing the entire field's reserves over decades. But the production engineer? They have a very short-term, highly focused intention. They are absolutely obsessed with specific wells, just trying to maximize production or injection in the most cost-effective way possible right now. And yeah, you better believe this sometimes creates a little bit of healthy conflict between the long-term strategists and the short-term optimizers. Section 2. Inside the petroleum reservoir, the underground reality. Now let's move deep underground to understand the physical constraints of the rock where these fluids actually live. So let's go ahead and shatter that whole underground lake myth once and for all. Hydrocarbons actually live in what you can think of as a rigid, rocky sponge. This concept is known as porosity, literally the ratio of pore volume to bulk volume. It's simply the amount of empty space a rock formation has to hold fluid. Because, well, if there's no substantial porosity, there's absolutely no reason to drill. And I want to give you a number to really put that into perspective. 0.3. Even in a fantastic, highly porous rock formation, maybe only 30% of it is actually empty space. And honestly, most are way, way less than that. So this means extracting oil is this meticulous game of fractions, literally squeezing fluids out of microscopic voids hidden inside solid rock. But here's the catch. Porosity is completely useless if those little pores aren't actually connected to each other, which brings us to permeability. Think of this as the microscopic tunnel system within our rock sponge. It describes the ability of fluids to actually flow through those interconnected pores. So you could have a rock with super high porosity holding a massive amount of oil, but if the permeability is terrible, that oil is completely trapped. No way it's getting out. What's truly wild to me is where our basic understanding of this comes from. Way back in 1856, a hydrologist named Henry Darcy wrote, "The flow rate of a fluid through a specific porous medium is linearly proportional to the head or pressure difference." He proved this just by running water through simple sandpacks in a lab. And get this, over 150 years later, the modern, multi-billion-dollar petroleum industry still uses Darcy's exact law as the absolute fundamental rulebook for fluid flow. And this perfectly illustrates how mixtures of hydrocarbons behave based on extreme pressure and temperature down in the deep earth. If the reservoir pressure is super high, like well above the bubble point, we have an undersaturated reservoir, which is strictly a steady liquid oil. But if that pressure drops below the bubble point, gas aggressively starts bubbling right out of the liquid, creating a saturated or two-phase reservoir. And if we're dealing with really hot, high-pressure gas that suddenly experiences a pressure drop, we hit this bizarre state called retrograde condensate, where liquid actually starts forming out of the gas. So the thermodynamics happening thousands of feet below us literally dictate exactly what we get up at the surface. Section 3, the near wellbore zone, the crucial bottleneck. Let's see how all this builds up to the most critical few feet in the entire system. Here is the exact step-by-step physical journey the fluid actually takes to escape the Earth. Step 1, it flows radially through that porous rock medium we just talked about. Step 2, it enters the near well zone. Step 3, it gets lifted up the vertical wellbore. And finally, step 4, it arrives at the surface separation facility. Now, to actually catch the fluid during step 2, while simultaneously holding back the crushing weight of the Earth, engineers use specialized hardware called well completions. Sometimes it's just an open hole, basically bare rock, but most often it's cased with thick steel pipe and cemented into place, and then perforated with explosives to make tiny little holes for the oil to enter. For really long horizontal wells, they might use slotted liners. And if the rock is kind of crumbly, they'll install what's called a gravel pack to filter out the sand so it doesn't clog up the whole multi-million-dollar system. But man, the incredible irony here is that up to 90% of the total pressure drop can occur just feet from the well. Why? Because of drilling damage. Think about that for a second. The very act of violently drilling the well often crushes and destroys the specific permeability pathways right next to the pipe. So we inadvertently create this massive bottleneck right at the finish line. Crazy, right?
Section 4. Journey to the surface, fighting gravity and friction. Because once the fluid actually makes it into the pipe, the fight is definitely not over. Now it has to climb.
Inside the pipe, the fluid is fighting two absolutely relentless enemies. First, friction against the steel walls. Second, gravity, specifically the hydrostatic pressure of literally miles of fluid stacking up on top of itself. Now, if the bottom hole pressure of the reservoir is incredibly strong, it can overcome all of that and just push the fluid right to the top. We call that a naturally flowing well. But if it's weak, well, engineers have to step in with some clever engineering hacks called artificial lift. They'll either drop mechanical pumps down the hole to physically push it up, or they'll inject lean gas into the well to literally lighten the fluid's density so it can just sort of float to the surface.
Section 5. Well deliverability, the ultimate engineering challenge. This brings us to the grand climax of production engineering. The crucial point here is the inherent tension between two very distinct systems. Production engineers are essentially playing matchmaker. On one hand, you have the IPR, the inflow performance relationship. This dictates what the underground rock and reservoir are physically willing to give up. On the other side, you've got the VFP, the vertical flow performance. That is what your physical pipe, wellbore, and artificial lift can actually carry to the top. Right there, where those two distinct curves intersect, that is well deliverability. By definition, it's the actual expected production rate of a well for a given operating condition. This single intersection is the ultimate scorecard for the production engineer. It quite literally dictates the financial and operational success of the entire multi-million-dollar project. So how does an engineer go about fixing a bad scorecard? By aggressively intervening. They can use matrix stimulation, basically pumping chemicals down there to dissolve that drilling damage we talked about earlier and repair the near-well zone. They can use hydraulic fracturing, creating these massive conductive cracks to completely bypass that near-well radial flow bottleneck. They can optimize the physical tubing size to reduce friction or implement that artificial lift to fight gravity. Their entire job is to mathematically and physically force that deliverability number higher. Which leaves us with a pretty critical question to ponder. As global energy demands continue to evolve, how will we push the extreme limits of thermodynamic and mechanical engineering to efficiently maximize extraction from the deep earth? Because as we've seen in this explainer today, sustaining this hidden, highly optimized energy infrastructure takes an absolute mastery of both earth and steel. Thanks for joining me on this deep dive, and keep questioning what's beneath your feet.